And yeah, so in this case, I will first discuss the second project. And the second project is on power transmission. So we will have to start this right after the midterm. So let me show you the requirements. We did upload the project description, and it is on the design of a power transmission system. So there's a short manual that you'll see, and the design project is basically to design a speed reducer. So the manual will go through the project statement, and then we have specific steps to implement various aspects of the project, going through determination of the gears, the specifications of the gears themselves, the number of teeth required, the diameters of the gears, the strength and the materials that are required. And then once we specify the gears, we will design for the shafts associated with the power transmission system. And the shafts will be, the design will be based on deflection analysis from what we learned in the class, and based on fatigue, and based on static stresses. And then once we design the shafts, then we're going to go into the attachments of the gears to the shafts, and that is the bearings, the keys, the retaining rings, and then we'll have a full layout of the power transmission system. So as you will see here, that we wanted to have a gearbox design that will transmit 25 horsepower, and it will have an input shaft speed of 6,000 RPM, an output shaft speed of 50 RPM. And then one of the requirements is that we wanted to have the input and output shaft to be intersecting at 90 degrees. And that obviously will determine the selection of the gears. As we will proceed in the project towards in the class towards the last few weeks, we will learn about the different kinds of gears. So it will be important that at least you have a look at the different types of gears ahead to be able to make the selections. And then later in the class, we will go more detail into the design equations related to the gear selection. But you will see that we will have spur gears, bevel gears, worm gears, and helical gears, so 4 different types. So here we have 90 degrees, which means that we will have to select at least one set of bevel gears to give us 90-degree angle. And then we have specific requirements. We want to select the shaft materials and the layout of the shaft, prepare free body diagrams for the shear force on the shafts, for the moments and for the torques, and then do stress analysis on all of the shaft locations that are critical, and determine fatigue lifetime. Obviously, and after the midterm, we will study fatigue in detail, but this will be part of related to this second project that we should start on. We also have a MATLAB program that you could use to determine deflections, and that is similar to the equations that we've been learning in this week and also in the next week. So the deflections of the shaft, we have learned a variety of methods. we've learned superposition, we've learned singularity functions, and we also are learning now about Castigliano's theorem. So there's a MATLAB code. If you have a step shaft that has different sizes, and the code is available for you, and you could use it to determine the deflection. So finally, we need a sketch for the gearbox and a solid model at the end of the project. So this should be a project that will be, the duration will be probably like 4 weeks after the midterm right away, 4 weeks of two of the partners in the same project that we did before, or we're doing right now on the connecting rod. That's kind of the main one. Then the gearbox project is much smaller, and it is, as I said, it's like a very long homework assignment that cuts across many elements of the material that we study in the class. So I will kind of let you go through the, once we put it online, which it is, after your midterm, then you will see that we've made an effort to help you by writing snippets of MATLAB code that you can fill in, or you can use, or you can mimic, so that you can complete that project on your own. So all of the variables are defined, and then you just kind of fill in and move from chapter to chapter. So this document will be, or it is online, and when you submit your report for this project, it will be as about 10 pages or so. And it would look similar to this report that I'm sharing with you from another student. And it was a master's question, so he did it basically in one long night. It was a 24-hour question that he passed, but it will be along the same lines. So he was able to actually type it, as you can see here. He put the problem specifications, one chapter on speed, torque, and gear ratios to determine the number of teeth and the diameters and the speed and the torque, and one chapter on the selection of materials for the gears based on two criteria: the wear of the gear and the bending. And then another chapter on shaft, and the shaft, the layout first, and then the force analysis and deflection, because these are the two elements for shaft's design: force and deflection. The force gives us the stresses, and the deflection gives us limitations on the deflections. And another chapter on stress analysis, and that you can use in fatigue, lifetime. And finally, bearing selection, keyway design, and retaining rings, and MATLAB. So that would be the final product that you will have on this project that looks something similar to that. I think you can see that you'll be able to type it and put in all the equations, and it'll be important to include the details of how you did the calculations on that project. So it doesn't have extensive software training like finite element or SolidWorks and multiphysics as we did in the connecting rod, but it is dedicated to connect all of the elements of the material that we cover, especially in the second half of this class. So that's an example, and I'm going to now give you another example on, or just follow up on the material that you will use to learn on your own for that project. So right after the midterm, as I mentioned, you're going to have to go to chapter 18 on your own as a learning material, as you can see here. So chapter 18 is on a case study for the power transmission, and the case study, it goes through the elements in starting from power and torque requirements, gear selection, shaft layout, forces, designing for stress, designing for deflection, bearing, and key selection. So it's exactly what I've shown you in terms of the requirements for writing your final report on the 9th week and to be submitted on the 10th week. So we're going to just do a little bit of introduction here to get things started, and then we will stop talking about the project and then shift to review of material relevant to the midterm exam. So for this project, for this chapter, the requirements were to transmit here's a requirement, 20 horsepower with input speed of 1750 RPM, and the output is very low, 82 to 88. So it's a speed reducer, and therefore, when something spins very fast, then the input gear has to be small. So it's the size of the gear is inversely proportional to the speed. So the faster the speed input, the smaller the gear. So we have a small gear coming in, and then the output speed is 82 to 88. So the gear size is going to have to be large. But we cannot do this reduction in speed in one step, because we have a limit on the ratio between the size of the gears. And the design requirement for this case study is for what they call an in-line design, meaning that the input shaft and the output shaft are in line, as you can see here. And therefore, we have to add a third shaft, and the third shaft is reverted. It means that we have the input shaft, and then we have an intermediate shaft, and then we connect it to the output shaft, as you can see here. So for this design, we can achieve the reduction ratio between input and output, or actually the gear ratio is defined as the ratio of the output speed divided by the input speed. So the output is 82, the input is 1750. So the ratio is like 1 over 20 or something like that. And 1 over, actually, if you just divide it, here, the input, it's 1 over 20.59. So that is for what we call compound reverted gear train, and that we have to make it in 2 stages, and the 2 stages would be the ratio of the speeds is the inverse to the ratio of the gear teeth numbers. So it'll be N2 over N3 times N4 over N5, and we make each stage to be equal so that we have efficient system, and therefore it will be taking the square root of 1 over 20 gives us a reduction of about 4.5 from the speed. So we're cascading from 1750 to something intermediate, and then from the intermediate again 1 more step to until we get to the output is 85. Now, for the selection of the number of teeth, that's the first step. We are limited by some minimum, otherwise there will be overlap between the teeth when they make contact. So the minimum, we have an equation, 1311, and the minimum based on this equation is 16. So in this case, we cannot go below 16 teeth. And therefore, we take the smallest gears that are coming in, the N2, to be 16, and the N4 also to be equally 16. And based on this ratio, then N3 and N5 would be 72. So that determines the number of teeth. 2 and 4 is 16, 3 and 5 will be 72. And once we have that, we can achieve this reduction ratio, 1/20. And we got all of the input and intermediate speeds. So the input speed is 1750, output turns out to be 86.42, and the intermediate is 388 based on that. So now we have determined the number of teeth. That's the first step. Once we determine the number of teeth, then we have to select the pitch. So the pitch is defined as the number of teeth per inch. And the number of teeth per inch is related to the height of each tooth. And that is related to the size of the gearbox. So we're going to have to take the gearbox limitation. So there's some size limitation that can take all of that. So if you go back to here, you see that the gearbox has it's like a box, as you can see, and we have to stuff in it a gear 2 and a gear 3 and a gear 4 and a gear 5. So in this case, and we have to leave a gap from the top and a gap from the bottom, and we have to also make sure that we take into account the thickness of the walls. So the size Y is given. So if we decide that we need to have the gearbox of let's say a 12-inch external size, that determines pretty much the pitch that we can use for completion of the gear selection. So the idea here is that if we look at Y, which is the external in here, it is going to be equal to a full diameter D3 plus half of D2. So if I take the gear D3 and I add the radius of gear 2, and then I add the radius of gear 5, which is D5/2, and then I add 2/P, which is from each side, we have the extent of the teeth will be added to the external dimensions, 2/P, and plus the clearances and the wall thickness, and that we equate it to the given size from the outside. And once we have the outside dimensions given, that can determine the pitch. So the pitch, as I said, is known as the number of teeth per inch. And for that solution here, the overall gear box height is 22 inches. It's a constraint. And based on that constraint for Y and the clearances, we have clearances and wall thickness of 1.5 inch. And we have determined now the number of teeth that can give us the minimum pitch required for the selection is 5.76. So we're going to approximate it to 6. And once we have the pitch determined, then the diameters of the gears are determined, because the diameter is the number of teeth divided by the pitch. So N/P for each one gives us the diameters of gear 2 and 4 to be 2.67, 3 and 5 would be 12 inches, And once the diameters are determined, then we can proceed to determine forces. And the forces, the idea here is that if a gear is rotating at a given RPM, then it has a tangential velocity called the pitch line velocity, which is pi d times omega. So this is the velocity of any point on that is tangent to the gear. And usually we write it in foot per minute. So foot per minute we divide by 12 because everything is in inch. So we get the what we call the pitch line velocities for the transmitted loads as the V of gear 2 pushing on gear 3. So V23 is computed from the diameter and the RPM to be here 12, 30, 23 foot per minute, and gear 4 on gear 5, 271.5 foot per minute. Okay, so now what's the idea of pitch line velocity? If we get the pitch line velocity, we know the horsepower, and the horsepower is the product of a force times a velocity. That's the simplest way to think about it. So the horsepower is product of the force times the velocity. So if we take the appropriate units, from the pitch line velocities, we can determine the tangential forces transmitted between gear 2 and 3 and 4 and 5. So at this point, we have selected the number of teeth for each gear to satisfy the transmission requirements for velocities. We have determined the pitch based on overall dimensions. We have determined the pitch line velocities based on the fact that the pitch line velocity is the product of the RPM times the diameter, or the times the perimeter. And from the pitch line velocity and the horsepower, we determined tangential forces between gears. So at this point, you should be able to go ahead and do force analysis. So we're going to skip that. And then you should be able to have a layout for the gears, because you know the sizes. Here are the sizes like you see here. And then you put a sketch for layout at that point to show how it looks like when it is connected together. So at that point, we have now sizes for gears, but we haven't done much analysis for the shafts. And therefore, we need to start from the forces, which we computed, tangential forces. And we have a contact pressure angle, which is the angle that the gears make when they transmit the force, is 20 degrees in general. So from that, we can determine radial forces as well. So for that point here, you will have the tangential forces, 2 on 3 and 5 on 4, and the radial forces, 2 on 3 and 5 on 4. And then you should be able to use the information we've learned to do force analysis. You have torque distribution. We have shear force distribution on the XZ plane, and bending moment distribution, and the same thing on the XY plane. So I think now this is as much as I would like to go on the second project, and it is something that will get started as soon as we finish with the midterm. And what I mentioned up to now, you should be able to do right after, like maybe right after the midterm, within the first week, essentially. Once you have this information, you should be able to make the selection for the gears, the layout, and then the force analysis, and then we slow down, and we will, once we continue learning more about fatigue design, then we can add more to that project. So now I'm going to switch gears to talk about the midterm and some of the homework assignments that we have. So if we take, let's say, homework assignment, this is homework assignment number 4, just a few comments on homework assignment number 4. So let me share the screen again. So we have homework assignment number 4. The idea for this assignment is that we have a couple of problems related to calculations of stress. But at that point in the course, we're shifting to more emphasis on deflection. So the midterm is going to cover from material selection, stress, and then deflection. So these are kind of the 3 general elements that we'll get in for the midterm. So homework 4 is just, we have a couple of problems, continuation of stress analysis, and then we have a few problems on deflection, and homework 5 has more problems on deflection, and then we have the midterm. So for this particular problem, we have a problem that has a latching spring, and it has a load of 3 pounds, and it's curved. So we have a radius of curvature of 1/8 of an inch, and we wanted to use beam theory to find the stresses right before the curved section on the straight section, and then we wanted to find the stresses around that curve in here, and find the ratio between the stress on the curve to the stress on the straight section. So on the straight section is very simple. We have to find the moment, F times the distance, and from the moment we use MC over I, and the top stress is going to be exactly the same as the bottom stress, but opposite in sign, no problem. Then when we use curved beam theory, so with curved beam theory, we have an inner radius of 1/8, an outer radius, you add the thickness of the beam, which is 0.1094. And we use curved beam theory to find the stress on the inner section, on the inner radius, and the stress on the outer radius, and then we just compare. So that's kind of the idea for that particular problem, and I'm not going to go any further unless there's any questions on this. So please stop me at any point if there are any questions that I can answer as I go on. Now I go to talk about the idea for the next problem, and this next problem is on a C-clamp. And C-clamp, you have a force 2,000 pounds, and then you have the C-clamp has kind of a groove in the middle on both sides, and the groove has a circular radius, and the circular radius here is 0.5 inches. So the cross section looks like an I-beam with like a groove circle, 2 circles on both sides, and we wanted to find the stresses on that section. So the idea for this problem is that we actually all what it is application of the equations for a curved beam. But in this case, the cross-section is a little bit complicated. It's not a rectangle, and it's not a circle. So how do we think about that? I think the main idea is to find the neutral axis, and the neutral axis has an integral, and the integral is the area divided by integral of dA over R. So this is kind of the integral. So if you think about the problem, it doesn't have really many complications except for finding that integral over a complex cross-section like that. So the way out of that is to think of the cross-section as the difference between two cross-sections, one rectangular, for which we know this integral, dA over R, which is B log of the outer radius over the inner radius, as we know from the lectures. And the other cross-section that can be used is a circle, because we have half a circle on the top, half a circle on the bottom. So when we put the two halves together, it makes a full circle. And therefore, we need to find the integral of dA over R for a full circle, and then subtract it. So to summarize, you can solve that problem finding the neutral axis by getting this integral dA over R for a rectangular cross-section, and subtract the dA over R for a circle cross-section. And in fact, that integral dA over R for a circle cross-section, you don't have to do it by itself, because there is a table 3-4 that can help to determine that for a circle cross-section. So that's kind of the key idea. You have the rectangle is B log R0 over Ri, R outer over R inner, and the circle is given from the book, and therefore we can use these two to reconstruct and get the neutral axis. Next problem is a problem of deflection. So now we finished pretty much all of the examples we needed on stress, and from that point on, our focus is on deflection. And that's pretty much going to continue for next week, which is in the next few days of the week, and then the exam will be at the end of the week. So you can imagine that there's got to be one problem in the exam on deflection. So the deflection, it starts with a simple deflection of straight sections under axial. So the deflection, you can think about it, either axial deflection, bending deflection, and shear because of shear. So we have these types of loadings that we will take into account. So that first problem is deflection under axial loading, but the cross-section is varying as a function of the length. So it has three sections, L1 and L and L2. And L1 and the L2 sections have constant diameters. And the section in the middle doesn't have a constant diameter. It goes from the small size D1 to the large size D2. So we want to calculate the deflection. And the deflection per unit length is F over AE times the length. The length is dx. So if we just take a small length, it will be dx. So for that part here, if we calculate the deflection for the first section, it is F over AE times the length L1. For the section on the right, it is F over AE times L2. But the one in the middle we have to do by integration, because the length incrementally changes from D1 to D2. Therefore, we have to put it in the form of an integral, F dx over AE, and then we write an equation for how the area changes from the left to the right as a function of x. So if we put a coordinate system on the first point where the cross-section changes, and measure the diameter as a function of x. The diameter as a function of x is the radius plus x times the slope, and the slope is tan alpha. This is an alpha, and then you do the integration and finalize the problem. Then next we start talking about deflection of beams. Deflection of beams, we have several methods that we studied, and in this problem we have two concentrated forces, and the problem has a limit on the deflection in the midspan. So it's here we have the deflection in the midspan is not to exceed ½ inch. So this is one limit that we have. And then also the maximum stress will not exceed 15 KSI as a design limit. So we have two design constraints that we have in this problem. And the requirement is to select a pair of structural steel channels. So like two channels, and you put them back to back so they look like an I-beam, but they're two channels. And once we select the dimensions, then we should satisfy both the deflection and the stress requirements. So for that, we just have to now assume that we have the loads and the cross and the moment of area. We can designate it as I for that at this point because we don't know the cross section, and then move ahead with finding the shear force diagram, the bending moment diagram. These do not depend on knowledge of anything about the cross section, but then we apply the first constraint, which is at the maximum moment, which is M2 in this case, the stress should not exceed the 12 KSI that's required. And that can give us some kind of idea about what is the modulus or the section modulus, Z. Z is actually second moment divided by C, which is the distance from neutral axis to top surface. So that can give us an idea about this. We can put it aside. And then we apply the deflection criterion. And in this case, we don't need to do a lot of calculations because we have a table that gives deflection for concentrated loads. We have two concentrated loads. Then we could use superposition to add the deflection of the first and deflection of the second. You can see it here. And that depends on I. We solve for I, the second moment of area. Now we have Z, which is the section modulus, and we have I. That can give us an idea now about what we should get in terms of the dimensions of the channels that we need for the solution. Now I'm going to now focus on, let me leave this for you to work on, to idea of singularity functions. So for singularity functions, when we study deflection problems, we put in the solution in terms, or the load Q in terms of singularity functions. And in this problem, we have a uniform load, and then we have also a concentrated load at position A. So when we write the moment equate, first we're going to get the reaction from statics, the reaction at O from statics. by applying the moment and the load here with reaction. And we started writing an equation for the moment distribution directly. So we're skipping actually usually we start from Q. We write it as equation that has singularity functions. And then from Q, we find V by one single integration. And then we find M by another integration. And then once we find M, we're just going to move on to find the deflection by two more integrations. Here we can write an equation directly for the moment because we determine the moment at O, and we have a concentrated force here that gives us a moment at 2000, like this is in meters, so we convert it to millimeter. So the moment would be one concentrated moment, one moment at O minus 9.5 times 10 to the 6 that we determined. And then we have the moment due to the distributed load and the moment due to the concentrated force that is put at 2000. So it's at x minus 2000 to the power 1 because it's kind of a linear function. And once we have the moment equation, we do one integration to get one constant, C1. The important thing to note here is that before we proceed to the second integration, we might as well determine C1 by assuring that the slope here is equal to 0. And once we apply the slope equals 0, it turns out to be that C1 is equal to 0. And therefore, we don't have to carry it any further for the integration. We integrate one more time to get C2 by imposing the condition that the deflection at x equals 0 to be 0. And that will solve for the entire deflection problem. So that's kind of what we have in terms, there's another problem using singularity functions. This problem here, the last problem that we have, and in this problem you notice that we have symmetry. So the middle section on the left and right is symmetric. So we can use symmetry condition to cut it in half and just study half of the beam from the left to the right. So here we have a step, we have a distribution on the step shaft, and we have to be careful exactly what's happening at that step of the shaft as we have in the videos. So in this case, we have to notice that the moment is going to be linear on the left because on the left we have a reaction. So we have a reaction here. The reaction times the distance is going to give us a linear function for the moment. And then once at that step, there's going to be an additional moment that is quadratic coming from the distribution of forces. But then we have, if we divide m over I, the cross-sectional area will change, and therefore the moment of second moment of area will increase, and therefore we have a step down because of the change in the second moment, and so on. So this is an important problem. I'll let you work on it. Very similar to what I covered in the class material. So now I'm going to just review a little bit about Castigliano's theory, maybe give you an idea about the midterm exam in reference to earlier exams. So I'll do another share here to show you what we have done in other exams. So this is special midterm exam that we had, and the midterm exam had 5 problems. So problem 1, we given the maximum allowable shear stress is 120, and we have a hollow steel shaft rotating at 2000 RPM. So we're given that if the inside diameter is 4.5 and the outside diameter is 6, then we wanted to know what is the power in kilowatt the shaft can transmit. So if we know the inside and outside diameters, we would know J for that shaft. And we therefore know from the allowable shear stress, if we have an allowable shear stress of 120, and we know J for the shaft, then we would know what the maximum torque is, because tau max is equal to T max R0 over J. And that already now gives us the torque, and the torque needed. If we have the torque and the RPM, then we would know the horsepower. So this is kind of a problem variation on knowledge for equations relating torque to horsepower to stress for the shaft. And it has also some additional questions on the stresses on the inside of the shaft, and if the shaft is 4 meters long, and we wanted to, if we limit the twist angle to 2 degrees, what would be the transmitted torque and power? So here we apply the idea that the torque is related to the twist angle. So this is another equation for torque, and limiting the twist angle gives us a limit on the torque, and again the torque and the horsepower formula that we have. So when we go in the midterm, as I mentioned, you'll be allowed to have 2 pages of summary, and the 2 pages of summary on your own, you will have the equations that will be necessary to solve this type of problem. The next equation is on material selection, and this problem. So we wanted to define the reduction in area, the degree of cold work, and we want to sketch equations, explain it. And also for B, it's more qualitative. We wanted to sketch Charpy impact energy as a function of temperature, yield and ultimate strength as a function of strain rate. And then the problem number C is that given some properties of the material, yield, ultimate, and the Romberg-Osgood parameters, sigma 0 and m, and we subject it to an 18% cold work, we wanted to find how much new strength and ultimate strength is obtained. So here you define the reduction area, the cold work parameters. We have in notes. You do the sketches for the Charpy as a function of temperature, the different strength of the ultimate strength, and the yield strength as a function of temperature. So this gives us an idea about qualitative understanding of material properties and relationships from chapter 2. And then we use the ideas that we developed to find the new ultimate strength from the old one using the cold work, and the new yield strength from the old one using the cold work, and the Romberg-Osgood parameters, the sigma 0 and m. The next problem is the Moore circle combined with stress in a simple configuration. So this is the idea. So the idea here is that I have a beam, but the beam doesn't have a symmetric eye section. So it has like one top here fat, and then the bottom is thin. And we have a bending moment of 200 kip inch and a transverse force of 5 kip. And we wanted to look at an element at the flange web interface, like here, the top flange web interface, and then draw the Moore circle for that element. In other words, we wanted to find the state of the stress in that element. So this problem has several steps. First step is geometry. So we have the geometric cross section. We have one rectangle on the top, one for the web, and then one for the bottom flange. And from that, we have to determine the centroid for each section. And from that, we have to be able to determine the I for the entire section. And we also have to determine the Q accumulated all the way to the interface based on that properties of the sections. So that's first part has to be done. And therefore, we just list the areas, A1, C1, A1, and so on, the areas and the centroid. So it's kind of a little bit longer, but if you know what you're doing, then you'll be able to kind of list it on the side. And once you have determined the properties of the areas, then you have the equation for I. And I now, we have to transfer all of the second moments to the common neutral axis by the parallel axis theorem. So you have I1 plus D1 squared A1 plus I2, which is for the web. That's, you don't transfer that. And then the bottom one, the I2 is for the bottom flange, and I3 is for the web. And therefore, you can get the total I, and that can give us the stress, bending stress, sigma A and sigma B, sigma C. So all of the stresses are known now from the bending. And then we compute the Q's, and then compute the taus. And then from that, from the stress, from the bending stress and the shear stress at the interface, we are able to find the principal values of the stresses using the Moore circle. So if you look at it, it's a systematic problem that requires a little bit of speed and organization, because you have to kind of look at the geometry first and find the moment of area for the entire section, and find the Q at the interface and prepare it, and then find the bending stress and the shear stress, and then apply Moore circle and put it together. The next problem is on the stress also, and this problem is also typical, in which we're given an interference at an interface between two shafts, and one is a solid aluminum shaft, and it's being shrunk fit into a hollow steel shaft, so one aluminum, one steel, and we wanted to find the highest and lowest interface pressure for that, because we have an inner, we have the hollow, the solid aluminum shaft doesn't have exact dimensions. It has 2.003 up to 2.006, means that it has this range of dimensions, and the hollow steel shaft has a range of dimensions for the inner, so from 2 to 2.002, and the outer is fixed at 3. And therefore, we have to kind of use our understanding to determine the minimum interference, the maximum interference at the interface, the minimum interference at the interface, And once we know that, then the highest and lowest stresses will be determined by the minimum and the maximum interference. And that would be kind of substitution in this equation. So it's basically, if you look at this problem, the key is to find the minimum and maximum interferences, and then understanding how to find the interfacial pressure. Once we get the interfacial pressure, then we can use the pressure vessel equations to determine the stresses. So here's the highest pressure, the lowest pressure, and then we use the equations of the pressure vessel to get radial stress and tangential stress. The last equation is Castigliano. So as I mentioned, we're going to have a problem on the midterm on deflection, most likely with Castigliano. And that's a problem here. We have like a link, rectangular member OB, and it's connected to a link CB. And then we have a force 200 at this location. We want to determine the vertical deflection at point B. So at this point, we have to make a free body diagram for the link OB and use Castigliano to find the deflection under the load. So under the load meaning exactly under point B. And in this case, we find the energy stored in bending and take the derivative with respect to the force. So we get the deflection as the dF by dQ, and I mean the deflection at point B here. We have to take dF by dQ times dF because we have an extension for this member here, CB. It will be under extension. So it will be the extension part, and then we compute the deflection based on the extension of that member in here. So for that, I think we have a pretty good idea about all of the requirements for the midterm, and I think the midterm is going to be somewhat similar, so we have an idea here, and we should be able to do very well in the midterm. So I'm going to stop my presentation here and ask you if you have any questions related to the homework or the midterm before we finish the session.
For the midterm, online I think it says that it's open book and we get the 2 notes. Is that true, or is it just the 2 note sheets?
Well, actually, the midterm is only the 2 note sheets, like the 2 pages, 8.5 by 11, just on 2 sheets. And then the final is going to be open book, because the final we're going to have a lot of equations, so we and design formulas and tables, so we're going to have it open book. But for the midterm, it'll be just 2 sheets, 2 8.5 by 11 that you can use for your equations.
And then is the second project also a group project, or is it singular?
The second project is also a group project. The same 2 partners on the first project will continue with the second project.
Thank you.
Okay. Any other questions?
Hey, Professor, I don't know if I heard you correctly. I thought you said, mentioned today that the midterm was going to be after homework 4 and 5.
Yes, because we have homework 4 right now, I think, that you're working on, but it has, part of it is on deflection. Homework 5, the first couple of problems are in deflection as well. And the lectures for this week were on deflection, and the first lecture on next week, which is before the final, will be on deflection on Castigliano. So the midterm exam will be covering all the way to the end of the deflection chapter.
So does that mean that the midterm's not this upcoming weekend, but the weekend after that?
No, the midterm is this coming weekend, right?
Okay.
because but what I'm saying is that the midterm, because the homework 5 has problems on deflection as well, and the midterm is going to cover up to the end of the deflection chapter. So you might as well, just you're doing problems now for homework number 4, which has a few problems on deflection. Review the lectures that I had on deflection. Just make sure that you cover the deflection chapter, and you should be fine for the midterm.
Okay, thank you.
All right, I think we're up to the end of our lecture today, and hopefully we'll do very well on the midterm, and then we'll see you on the next meeting.